Hi everyone, I'm Hemendra Sharma. I work as a platform engineer at SquadStack. So let's get started. So the topic for today is like Postgres as a message broker to handle asynchronous tasks at scale. So first of all, why did we choose to use Postgres instead of any other, let's say Redis or RMQ? So this is our agenda. First, I'll be explaining the use case, like why we are using Postgres. Then before Postgres, we were using RMQ for asynchronous task handling, and we have faced some issues. So the second point will be related to that, what issues that we faced in RMQ. Then third point is PGQ introduction workflow. PGQ is basically Postgres queue. We call it in short as PGQ. After that, how tasks process, the components and issues that we faced in PGQ and how did we solve them. And that's the conclusion. So why did we use Postgres as a message broker? So let's first start with the issue in RMQ. So in RMQ, we often face RAM overload issues as in asynchronous tasks, we all store task data in RMQ. So sometimes when we get messages in bulk, it started causing RAM issues, due to which we need to find some solution. We also try to debug the issue. After some time, it also start occurring, multiple times it start occurring. So we even increased the cluster size of the RMQ nodes. Even after that, it was not fixing. So that's why we thought we should use something else. Also, there were some many other issues also, like we have in the RMQ, we have limited observability and cost inefficiency. So observability or monitoring in RMQ is that I only get a very few metrics, like the ingestion rate, the consumption rate, and basic general information related to tasks like their size and all that stuff. But we needed a lot more than that. So in PGQ, we have basically all the tables in SQL, so we can query any data that we want. So we have a much better observability at there. And the third one is cost inefficiency. So as I mentioned, when the issue occurred, we even increased the cluster size. That was almost double the cost of that previous one. So that was very cost ineffective. So in PGQ, we using a simple M702X large instance. With that, we able to reduce our costs for the asynchronous task operations. And then a fourth point is the limited customization. So basically in RMQ, we can't do any customizations. In PGQ, we can do anything because we made from scratch. So we can do any customization. Like if I wanted to, from some metrics inbuilt, I want to do some auto scaling. So I can do that in the PGQ. So PGQ is basically custom task queue built with Postgres and Django. It's quite reliable, scalable, and have much better concurrency control. So PGQ supports periodic task and ETA-based task with retry mechanism. I'll explain each one by one. So periodic tasks are basically cron tasks, which we have created. So it executes crons. ETA-based task is basically delayed task. Let's say if I wanted to execute a asynchronous task after operation, after 1 hour of operation, like after a call, I want the task to execute just after 1 hour. So I can give a pickable at field. So based on that field, it can execute after that 1 hour time. And retry mechanism, like if I wanted to have custom retry, like I know if some API will fall, then I want to retry the functions, so I can do that too. We also have a sidecar process to manage the PGQ consumer workers. So I'll explain the sidecar process in the next section. So basically this is the basic overview of the PGQ. So on the left, you can see there are producers, and producers basically are backend servers. They will send the task-related data, like task ID, queue ID, which is necessary for the task execution. Also pickable at and retry count. They will send that data to Elastic Cache. Elastic Cache is basically a Redis instance. Now, so from Redis, we have a trigger schedules. So like schedules will trigger the Lambda functions, and they fetch data from Elastic Cache in batches of 1,000 or 2,000, and then bulk insert into the Postgres database. So now till this point, all the data has been reached to the Postgres. Now producer part is completed. Now we have the second thing, like consumer section. So consumers have basically two type of services. One is a consumer runner and another is a sidecar. So basically consumer runner is a systemd service that fetches tasks from DB in batches using select for update skip log and process them. Also for the sidecar basically just monitors the health of the consumer workers. So it basically syncs the IP address and the process ID of the worker with that a table in the database. And if there is any discrepancies, then it will update the status of the task that is in the failed state or that is basically abandoned. Yeah. So this is the general how task process in PGQ that I explained. So first of all, task creation. The task producer creates the task, then the data transfer to the Redis, then Lambda fetches the task from Redis. After data has been reached to the database, the consumers will retrieve the task in the batches of usually 10. We can modify it also, but 10 is better size. And then using select for update skip log, we fetches all the data and start processing them. So this is general schema of the tables. In middle, we have a task instance table that has like task ID, queue ID, params, and other things. Params basically store the arguments of the function that we want to call. Let's say if a function like add 2 or 2 plus 2 comma 3, which will add the function. So I'll send all those parameters in the param section. And it has like retry count, visibility timeout, worker ID also. So visibility timeout, like if I mention it 30 minutes, so after 30 minutes of getting picked, if it's not executed, then it will fail. If we customize this, we can also like send it, change its status to pending, but we thought failed will be better choice. And then on the right, we have task, which stores necessary information like name, module, created at, and updated at. So task basically store all the information that is necessary to execute the task. Like it will give us a module of exact path. From that, we can execute the task. On the left, we have task query and task queue and worker. So task queue basically stores task-related information, and worker basically stored the consumer worker, that service that I previously talked about, there's information. So yeah, basically it has 4 components. We talked a brief about producer, consumer, and sidecar. Cron runner, I'll explain the upcoming slides. So yeah, producer, same stuff. Like it helps in creating tasks. It pushes data to the Redis. Like with necessary params, it has a fail-safe mechanism. So for any reason, if Redis fails, it will directly send data to the Postgres. Although that's not optimistic, but optimized. But that's in case of failure, we can do that. So our data will not be lost. And then we have a retry logic and reliability. So as I explained, we can customly retry the functions based on certain conditions if you want, like it's customizable. And then we have reliability. So even if something happens, the data will stay in the Postgres, right? So in case of RMQ or any Redis, let's say if something Redis server crashed or anything happened, all the data will be lost. Now we have the second thing, the consumer, that fetch the task from DB and process them. That's the thing we explained. One more thing in a consumer is queue flexibility. Like if I want to execute all queues, I can do that. And if I want to consume consume specific queues, so I can do that by giving a parameter. So this way, there's a specific issue we faced. So I'll explain that in the issues section related to this. Yeah, so basically the thing I explained previously, we have 2 services. One for to run all the queues, basically to fetch data or task from all the queues, and the second one is from specific queues. So we can fetch data from specific queues too. So this is a general snippet of the code that we use. So it's you see the third line queue ID in equal to queue ID. So if we pass the queue IDs, it will fetch data from the that specific queue IDs. Yeah, now to cron runner. So basically, cron runner will be responsible for the cron task in PGQ. So the cron runner will use the salary beat that will, with a custom scheduler, so salary beat will push data to the Redis with the specific tag, like in our functions, if we define run every field, it will fetch that cron job from that, and according to that, it will create task based on the run every field. That means cron job. Yeah, so it has 4 sections: task scheduling, task queuing, buffer handling, and task execution. So in task scheduling, the salary beat uses the periodic task model, which is there in the salary beat, and it will send to a local Redis. Then from local Redis, we have a cron runner systemd service that fetches the task and send to the elastic cache, or similar to that normal asynchronous task. And then all the process will happening like task execution, like that I explained before. So yeah, now to the sidecar. Sidecar basically monitors all the consumer runner processing running on that. So let's say if example, a consumer worker has failed due to some issues like CPU or RAM issues. So what the sidecar will do, it will fetches the IP address and the IP address and the process ID of the consumer worker, and it will fetch and it will sync with the worker table in the database that I previously showed. And if there is any disturbances, then the task that is picked by that specific worker will get retried. And the worker that has the killed, it's marked as inactive. Yeah, so this is the final architecture, final overview of the diagram. We have producers, elastic cache, then lambda, and then the 4 tables that I talked about. And below you can see in the consumer runner, you can run the failed task also. Yeah, so this is the part. Now the main section related to the Postgres, the issues we face in the PGQ. So the first issue we face is high API response time. So basically what happened when we shipped this feature, we saw the response time of some APIs get increased. Why is that? Because the DB load has increased over the time, and inserting and reading the queries was taking some time, like 1 or 2 seconds was increased. So that was the overview. And for the second one, the task starvation. So if let's say for a single queue, if there will be many insert operations like 1 or 2 lakhs on one go, then the consumer workers, the common one, will start fetching from that queue, leave the other queues starved. So that was the second issue that we faced. And the third one, basically, lock manager wait events. So basically, we face many wait events related to lock manager, and it increased the DB load to 2 or 3 or 4x times. So I'll explain each one in depth. So first one, high API response time that I explained. So analysis. So this was happening because we were inserting data one by one in the first version of that. So as we know, if we insert data one by one, so it will cause contention everywhere like buffer, val, or block manager 2. So we see LW lock transaction ID wait event. So we knew we need to fix this. So for that, what we used, we introduced a buffer in between. So as in the previous slides, you saw we have an elastic cache. So we added elastic cache because of that. So now from this point onwards, all the queries will go to elastic cache, and then from elastic cache, using a lambda, they will bulk insert into the database. So this problem we solved by using basically elastic cache or buffer. Yeah, this is the section that I explained. Also, our workers were using select for update skip log, so that is quite, it will cause a lot of locks, due to which also this transaction ID happened, but wait event occurred. So as you can see on the screenshot, it was using 25 vCPUs, only the insert operation only. So after the fixing of this buffer issue, it was gone, like this wait event was not coming at all. So now let's move on to the second issue that we face, task starvation. So in that, when low volume queues are delayed because our consumers were waiting for working on the high volume queues. So this is a scenario that I explained. If a queue receives a large number of tasks, the consumers start processing from them, leave the other queues empty, unattended. So this results in starvation of few queues, like few high priority queues. So how did we solve this? So we seen like there are 3 or 4 queues which are very high volume queues. So we separated them from common consumers. As I explained, we have 2 types of services. One is run for common, like for all queues, and one for specific queues. So even though if I separated the queues for high volume queues, they're still coming into the common queues and starved them. So basically, we just removed them from the common queues, and this issue was solved. So that was the customization talk I was talking about. So here we can customize anything based on our needs. Yeah, this is the sample code for that. The first line you say PGQ consumer queue exclusion. These queues I removed from the query, which is the fetching task ID one. Yeah, and now the final one, lock manager wait events. So first of all, what is the lock manager? So lock manager handles all the logs related to the Postgres, all the relations like tables, indexes, etc. So basically how lock manager works is it uses 2 mechanisms. One is centralized lock manager one, and one is fast path mechanism. So centralized lock manager is basically for the heavyweight logs. So basically they will go to the shared memory of the Postgres and update the log status from there. But to do this for everything is not like possible, right? It will take too much logs and stuff for this to work. So Postgres has a feature like called fast path mechanism. So where when a connection is established, it created a slot, like basically 16 slot, which is defined by FP log slot per backend. So it will not go to the central lock manager for the lock management and do it from on the same connection also. It is separated by connections or backend processes. Also, one thing to note here is it's for unique logs per log per relation for every relation. Like if I have a relation, like if I have an index 1 and it has 2 logs. So FP log slot per backend will use as a 1, not 2. So the issue was in our PGQ, basically we started a transaction and then we start fetching queues and start executing them. So we had some extra indexes or unused indexes, due to which the total limit of 16 was exceeded. So because of that, we have seen a huge increment in the LW log manager wait events. And due to which CPU increased almost 3 to 4 times. Like basic, we have vCPUs around 16, and it increased DB load to almost 50 to 90 in that range. So at first, we see this issue in one go, like you can see in the screenshot. Then after that, it will start coming, and even after that, it's also increasing. I don't have screenshot for that, but yeah. Then we did some debugging, read some logs related to that. So in this screenshot, you can see it's fetching data from that PG logs table, and it shows the total number of fast path, which one are using fast path and not. So you can see 16 were using fast path and 6 were not using that. Yeah, so in screenshot you can see after the 16th log, from the 18th log, it start using the central lock manager one. It was not using fast path mechanism. So yeah, how did we solve this issue? First of all, we reduced unused indexes and unnecessary indexes and queries inside transaction. So basically, if this happens only in case of transaction, right? If I remove some unnecessary queries or unnecessary indexes, then I can avoid the FP slot backend, number of slots in that inside in them. After that, as I explained, we avoided some queries in the transaction. So overall, we reduced transaction time. And if you find some DB parameters like Maxwell size and effective I/O concurrency to increase the concurrency of our database, because our use case is have too much concurrencies there, because we run almost 200 to 300 workers, consumer workers, for fetching the task. So imagine how many logs will be there. And fourth one is just a optimization thing. So we purge all the data, like 1 day before data, and reindex and vacuum properly, so that we won't face any issues. So this was after all the optimizations. As you can see, first of all, we used M6.4x large instance. Then after optimization, we see like we optimized too much, so we even decreased it to M7G.2x large. And you can see the max vCPU is 8 for this case, but even though our tasks were running fine, it's only using 2 or 3 vCPU max. And the worst case, it will go to max 6 or 7 something. So yeah, this was the main conclusion. So basically, we scales well without excessive RAM consumption, as I explained. And now we have provide better observability via database queries. I can query anything. Like if I want to, let's say, find out which tasks are taking average time, P90 time, anything, or if in any task I can see their params. Like in RMQ or Redis, I won't able to see params properly. Like it's a little bit difficult, but from the SQL query, I can fetch any data that I want very easily, and it ensures reliability and with failure handling. Also, it's cost effective. We reduced infra cost by almost 50 to 60%. And we have also custom scaling for this. So we have, fetched all the custom metrics. From those custom metrics, now we are working on auto-scaling the consumer runners. So this was little bit difficult in case of RMQ. As we haven't removed that, that extra queues that I was talking about, heavyweight queues. So with that removal, we solved the problem that helped us to, create metrics that will be helpful in auto-scaling. And also one more thing, like in all the data is stored in the Postgres, right? So if I want to debug something, like if I want to debug, let's say for a specific task, why it's taking, so much time, what its parameters are there. So I can directly fetch from the task table. Also, if for failed tasks, we can do this for failed tasks too. We can fetch data for failed tasks and see what went wrong in that. So yeah, that's it. Thank you.